All right, so the first talk of this session is actually kind of a combined talk of two separate papers. What is the title then? So there's a joint title, I guess, Approximation Schemes for K-means, K-median, and Other Clustering Problems via Local Search. And we have two speakers, one from each paper. And Zachary will start?
No, I'll
Vincent
start.
will start. Okay.
Okay, thank you. So so my paper is a joint work with Phil Klein and Pierre Mathieu, and Zach's paper is with Moshe Rezapour and Mohammad Salvatpour. Okay, so this talk will be about clustering problem and a very simple local search algorithm. Okay, so first, what's clustering? Well, clustering is to partition data according to some distance function. And so one example is to partition buildings so that you can find the best spots for your fire station or your warehouses or this kind of thing. So one example that is in textbooks is you have a map of a city and then you want to find the best spots for your fire station. Okay, you also have a new application in machine learning, image compression, these kind of things, where you have data in a low-dimensional Euclidean space, and then you want to group data, partition data, according to similarity. Okay, so what is clustering more formally? So historically, people have been looking at the K-median and K-means problem. And here in this talk, we would like to look at what's called the K-clustering problem. You have data points in a metric space, and you would like to find a set of K centers that minimize this objective function, which is just the sum of the distances of each point of the data set to its closest center to some power p. And let's think of p being a constant. And when p is equal to 1, then you have the K-median problem. When p is equal to 2, you have the K-means problem. Okay. And then when you have the set of center, you can just compute the clustering by looking at the partition induced by assigning each point to its closest center, and this gives you a partition of the data. Okay. So what's the story? What's the history of the problem? The problem, so the K-median problem was introduced in the 70s. It was shown to be NP-hard. Then there were like some results. First the log n, log k approximation, and then the first constant approximation is in 2002. Then in 2004, people showed a 3 approximation, and this was by the same local search algorithm we will analyze today. And later, more recently, it was even there were better results below 3 using LP rounding techniques. Okay, but the thing is that this K-median problem is NP-hard. It's NP-hard to get something better than 1.735. So it's a hard problem in the general case, for general metrics. Okay, and the K-means problem, there are less results, but what's known is 9 in Euclidean and 25 in general metrics. And again, using this very simple local search algorithm we will analyze today. And it's also epi-XOR, so you cannot have a p-task if you have at least log n dimensions. So it's a hard problem. Okay, so when you're facing a hard problem, what you could do is to get good results is to look at more restricted inputs and hopefully inputs that are still relevant in practice. So what are the inputs that are relevant in practice? Well, as I told you, you might want to solve this problem to locate fire stations. So in that case, you have road networks, and then this can be modeled by a planar graph. And also you have low-dimensional Euclidean space, and these are relevant input in image compression and machine learning. So what are the results for those type of inputs? Well, for planar graph, it's very frustrating. Nothing better than the general case is known. So we don't know how to exploit the structure of planar graph to get good approximation guarantees for this problem. Also, in low-dimensional Euclidean space, the situation is a bit weird, I found, because since the 90s, you have a 1 plus epsilon, a p-task, 1 plus epsilon approximation for K-median, but nothing better than for higher dimension is known for K-means. So it's really surprising that if you start raising this p above 1, you get different results. Okay, and there have been some results on that. So 1 year ago, Claire, Mathieu, and I, we showed that local search, if you allow it to pick up to 1 plus epsilon time case center, so just cheat a little bit, then you can get a 1 plus epsilon approximation for k-median in low-dimensional Euclidean space. And this was later improved this year, extended to the k-means problem in low-dimensional Euclidean space. Okay, so those two results are interesting in the sense that they show that in practice, since people do not care too much about the exact number of centers, they can use those heuristics to get 1 plus epsilon approximation. Okay, but the main open question here are obviously, can you get 1 plus epsilon approximation for k-means in low-dimensional Euclidean space using exactly k-centers? And what can you say about planar graphs? Okay, so here are the results.
Okay, so our group, we get a p-task for k-means and k-median in doubling metrics.
Okay.
So doubling metrics include constant dimensional Euclidean metrics, and I'll define them in my half of the details.
Okay, and in our group, we get 1 plus epsilon approximation by local search for low-dimensional Euclidean space, but it also extends to H minor free graphs. So it doesn't work for doubling metrics, but it extends to H minor free graphs. Okay, and we got also some extensions.
So some extensions that bear mentioning. For uncapacitated facility location and for k-means or median with opening costs associated with the centers, we get a p-task in doubling metrics for this case as well for non-uniform opening costs as well.
Yeah, so in our case, we got the first p-task for uncapacitated facility location with uniform opening costs in H minor free graph, so this was known. But the thing is that doesn't extend to the non-uniform opening costs. Okay, actually you can show that this algorithm will not work. So this is actually an open question whether you can get something better for non-uniform opening costs in H minor free graphs. Anyway, everything we say here work for p being some constant. And actually, yeah, that's it. Okay. Okay, so what's the local search algorithm we are going to discuss here? So it's the very naive algorithm, right? You start with any solution. Okay, so a solution is basically a set of centers. Then you try to remove a constant number of centers and add them back at different locations. And then you obtain a slightly different solution, and you ask, is it the better solution or not? So if yes, well, then you keep that solution, and then you start again this whole process of trying to improve the solution. Okay? Otherwise, you just revert back to your initial solution, and you try another set of changes. Okay? You try two different changes. Okay? And you stop whenever you cannot improve. Okay? So the number of center you will remove and add will be a function of epsilon. Okay. Okay, so now I'll present the results that we got in our paper. Okay. So we got this theorem. So this is the stronger version of our theorem that local search with if you are allowed to swap in and out 1 over epsilon to some constant centers at each step, then you will achieve a 1 plus epsilon approximation for the k clustering problem in H minor free graphs. Okay, and it also extends to low-dimensional Euclidean space, but yeah, this is one of the two theorems we got. And in this talk, I don't have time to tell you much more than this simpler version, this slightly weaker version of this theorem. But if you understand this simpler version, then when you look at the paper, you will understand it's not much work to understand the much stronger version. Okay, so in this simpler version, we show that if local search is allowed to cheat a little bit, so meaning opening 1 plus epsilon time k centers, then you can get a p-task for k-median in planar graphs. Okay. Okay, so now let's look at this proof. So this proof is very clean, very simple, so everyone could understand it, I think. So okay, so for notation, let L be the solution output by local search using up to 1 plus epsilon time k centers. All right. So what's the proof? So the proof is in 2 steps. Okay. So the first step we will assume that there exists a highly structured optimal solution, such that for the first step, we will use that solution to analyze the cost of the local search algorithm. And in the second step, we will show that this highly structured solution exists. Okay, so first, let's assume that there exists this highly structured solution op star, okay, such that you can partition the graph into regions, such that each region has few centers of the local and the op star solution. Okay, so if you look at this red area, this is not a region because it has many centers of the local solution, right? So this is not a region. Okay, those two blue areas are region for now because you have like few centers of the local and few centers of the op star solution. Okay, and the second condition is that what happened in one region is independent from the rest of the graph. Meaning, if you take a data point in the region, then it is served by a center of op star that is in the region. Okay, so for example, this red area is not a region because if you take a center that is here, for example, it's actually closer to that center of op star that is not in the region rather than this center of op star that is in the region. Okay, so you really want to have independent region, meaning that points in one region are served by a center that is located in that region. Okay, so for now, suppose that there exists such a structured solution op star that has at most 1 plus epsilon time k centers. Okay, so if we assume that, we can now analyze the cost of the local search algorithm very easily. Okay, so let's look at the cost of the local search algorithm in one region. Okay, so let's define a mixed solution, L prime, that inside one region, this blue region, you pick the center of op star. Okay, and outside the region, you pick the centers of the local solution. Now, there are few centers of L and op star in the region. So the difference between this L prime solution and L is at most a constant. Okay? Just because this is by definition of the region. All right? So now, if the algorithm stopped with the solution L and not with the solution L prime, it means that the cost of L is at most the cost of L prime. Okay? Because the difference between the two solutions is so small that the algorithm has tried to get this L prime solution, and when he looked at it, he didn't pick it, so the cost of L is actually smaller than the cost of L prime. Okay? Okay, so what does that give us? Well, we have this nice equation, cost of L smaller than cost of L prime, so now let's just look what's inside this equation. So the cost of L prime, because of the region are independent from one another, can be written as the cost for the client that are in the region. It's at most the cost in op star. For the client that are outside the region, it's at most the cost in the local solution. So the same thing for the local solution. For the client that are in the region, it's the cost in the local solution, and outside is the cost in the local solution because it's the local solution. Okay, so now you just plug those two inequalities into that one, and what you have is that the cost of the local solution, since the cost of the local solution is at most the cost of the L prime solution, you end up having that the cost, just simplifying those two terms here and there, you end up having that the cost of the client in the region is at most the cost, the optimal cost in that region. Okay, just simplifying the two terms. All right. So this is a very simple argument, and it gives us that now if you sum this argument over all regions, sum this equation over all regions, you end up having that the cost of the local solution is actually smaller than the cost of the op star solution. So you get actually an optimal solution. Okay. So now here the main issue is that to ensure that the algorithm run in polynomial time, you want to make sure that at each step you make a significant progress. So this will force you to lose a factor of epsilon opt. So that's why you get a 1 plus epsilon approximation. But if you could run the algorithm long enough, then you will actually get optimal solution. Okay. All right. So really, the main idea here is to define this solution op star that has few centers in each region, so that in each region you have few centers of op star and L, both, and the region are independent. Okay, so points that are in one region are served by a center in op star that is located in that region. All right, and you want that op star is not too big compared to K. Okay, so now let's let me explain how you can why this OpStar solution exists, right? Like for now, I just assume that it exists, but I should justify that it exists. Okay, so let's look at the local solution and the optimal solution, opt, and define OpStar. Okay, so let's look at the clustering induced by the union of the local and the optimal solution. Okay, so this is the clustering induced by those two solutions. So you have, say, in pink, the optimal solution, in black, the local solution. Okay, and now we look at the clusters. So the cluster are the areas in color. You look at the clusters, and we contract each cluster to a single point. Okay, so let's contract this area, this green area, to a single vertex. And if you do that for each cluster in this picture, you will get this graph. Okay, just contracting things. Okay, and so this graph is still planar because planar graphs are closed and are contraction. Okay, that's easy. All right, but okay, so why is it interesting to look at this graph? Well, because this graph has a very nice property that we call separability property, which is very easy to understand. So if you take a set of centers that is a separator of the graph, so that if you remove them, you disconnect the graph, then you have that any point that is in one side of the separator is actually closer to a center that is in the separator than to a center that is in the other part. So this is very easy to see, because if you look at the uncontracted graph and you look at the client here, a point, and you want to reach a center that is in the other part, then you start walking, but at some point you will cross this green area. And once you cross this green area, you know that you are actually closer to a center that is in this green area rather than a center that is in the other part, right? Just because the definition of clusters, right? You know that you are actually closer to that center to any other center. Okay? So you have that point in part one here in this drawing are closer to a center of the green area than to a center of part two. Very, very simple property. Okay, so if you look at the bigger picture, if you take OpStar to be opt union the green separator here, you have the data point that are in one side of the separator are served by a center of OpStar that is either in this part or in the separator. Okay, just because what I explained before. Very simple property. Okay, so now we make the final step, and this is the end of the proof. And we use a simple property of planar graph, which is very well known, very old. Everyone heard about that. This planar that we have planar separators, so small separators. So for any planar graph with n vertices, you have a balanced separator of root n vertices. Okay, so we will use that. So how do we use that? We apply this argument recursively. And what we end up with is a partition of the graph into regions that have a small number of vertices, 1 over epsilon square vertices in each region, and the total number of vertices that are on the boundary of the regions, okay, at the interface between the region, is at most epsilon k. Okay, just applying this balanced separator idea recursively. Okay, so we do that on the graph where you have contracted the clusters, okay, the graph I described before. And what we have is that if you look at one region, a client that is in one particular region is actually closer to a center that is in that region or to a boundary, to a center on the boundary. Okay, so now let's define OpStar to be the optimal solution, union the boundary vertices of this division of the graph. Okay? And now you have the desired property that this OpStar solution has, so now you have a division of the graph into regions that have few centers of L and OpStar. And OpStar is not so big because you know that the total number of boundary vertices is bounded. And for any region, you have that data point in one region are served by a center that is in that region. Okay, so that's the thing. So this completes the proof for the graph case. And actually, the proof for the Euclidean case is very nice because it's exactly the same proof. So you don't have to do anything else, any more work. It's actually copy-paste. You have you just use the theorem by Battiprolu and Harper-Led from this year at Sausage, that there exists this division of the Voronoi partition of a set of points in the low-dimensional Euclidean space, and it works directly. Okay, so I stop here.
Thank you very much, Vincent. So I'd like to talk about our work now in our paper called Local Search Yields a P-Task for K-Means in Doubling Metrics. And as said before, this is joint work with Mohsen Rezapour, who was a postdoc in our department at the time, and Mohammed Salavatapur. A quick reminder where we're at, and maybe to set up my notation, is we have a collection of data points A, possible center location C, and an integer K. And we want to find K centers, L, to minimize the sum of the squares of the distances between data points and their nearest open center. And the local search algorithm is quite simple. We'll start with any K centers in an arbitrary set, and while it's possible to exchange up to some constant number of centers, we'll fix this constant delta later, and get a better solution, do that. And when you can't find any such improvement anymore with your current solution, we'll return it, and we call that our locally optimum solution. So what we show is that if you choose this particular constant delta, which I guess it's like epsilon to the negative d over epsilon, then you get a 1 plus epsilon approximation for k-means in d-dimensional Euclidean space. And more generally, this extends to doubling metrics with dimension d. So we'll say that the doubling dimension of a metric is d if any ball of radius, say, r, can be covered by 2 to d balls of radius r by 2. And doubling metric, we'll just call it a doubling metric if you can regard the doubling dimension as a constant. And doubling metrics include constant dimensional Euclidean metrics, but another neat example is Manhattan distances in r to the d. So we get a p-task for this case. So our analysis is enabled by, I think it's a fairly new partitioning scheme. So let me tell you what this is. So let's consider the local optimum solution the algorithm returns and some fixed global optimum solution. We'll consider them jointly and assume they are disjoint. That's safe to assume. We can partition this set through some random partitioning scheme to ensure that we get parts of constant size, this constant delta, and their balance between the local and global optimum solution. So the parts of the partition define valid swaps. The local search algorithm would have tried that swap and then saw that it's not an improving swap. But what's more important, what's also important is how we can use these swaps to bound the client, the center, the data point assignment cost. So what we can prove is for any data point with probability 1 minus epsilon over the random partitioning, well, for any data point, if you look at the part, maybe just listen, if you look at the part that contains the local optimum center serving it, well, that part will also ensure that after you swap the part, there's something really close to the local optimum center or something really close to the global optimum center. And really close is this negligible quantity, epsilon times the total distance this data point moves between the two solutions. If you're used to local search analysis, this is extremely handy because when we try closing this center here, well, either we don't have to move very far, the cost change is negligible, even if the squares of the distances measure. Or else we can say that the cost change is bounded by the cost change to the global optimum center minus the local optimum center, again, the squares of those. And any extra distance you have to travel is negligible under any constant power of the distances. And finally, we need to have this reasonable backup plan. What if we're not in this good situation for some particular point? We need to have something sensible to do. So we also show that with probability 1 for any data point, in the part that closes the local optimum center serving it, it has to travel some constant times its total distance between the two solutions. And recall that we'll only invoke this backup plan with probability epsilon for each data point. So I don't want to talk too much more about how we use this in the local search analysis. That's fairly straightforward. I want to talk about how we get this partitioning scheme. And we'll just get this through a sequence of fairly elementary but well-coordinated steps. And the heart of the matter is just using a random grid. So we'll start by defining a radius around each center between the local and global optimum solutions. And it's just going to be the distance to the nearest center of the other type. So for every global optimum center, it's the distance to the nearest local optimum center, and vice versa. So that's the radius of a center. And now we're going to thin out the set of centers, temporarily discarding some. So we're going to, using some standard filtering, we're going to discard some centers, again temporarily, so that the distance between any two remaining centers is at least epsilon times the radii of the centers. But for every center we discard, there's something nearby of the same type. So for every center I we discard, there's some other center I prime of the same type that's distance at most epsilon times di. So for example, this grayed out blue dot is really close to that solid blue dot. This is convenient for us because they're fairly well separated, but they also still form somewhat of a net for the set of centers that are actually serving the data points. All right, so they're thinned out now, and you can just use standard filtering if you know these things. Now, before we get to our random grid, there's a particular matching on the centers that I'd like to point out. So let's just let phi be this function that maps every surviving center, so they survive the filtering, to the nearest surviving center of the other type. Now look at, say, a local optimum center, and look at all of the global optimum that map to it via phi. And let's pick on the closest one. If it so happens that the radius around I is at least epsilon times the radius around I prime, I want to declare these two matched. And this is my matching. Otherwise, I don't care about matching them. In fact, I don't want them matched. So with this matching in mind, we see something very convenient that as long as we ensure that both endpoints of any matched pair are in the same part, then we get our reasonable backup plan. And briefly, it's just because if the center for J gets closed in a swap, it just marches along the phi mapping. Just keep following until it hits either an open center or it hits a green edge, in which case it goes to whichever of the two is actually open. Every other step decreases in length geometrically, so we get our reasonable backup plan. And because if it's not a green edge that we hit, then we know the distance will decrease by an epsilon factor. Okay, so with this matching in mind that we want to maintain, we use our random grid. For the moment, suppose that the aspect ratio of the radii are bounded, so all the radii are between 1 and some large constant. We'll just consider a random grid with slightly larger constant width. And the cells of this random grid define our initial partition. It's not the final one, but it's the initial partition. And if we happen to cut one of these matching pairs that we wanted to keep together, let's just move the global opt part to the local opt part. So we're not moving the points, we're just tweaking the partition. But that will happen with probability epsilon, at most epsilon, for any matching edge. A very simple volume argument, which is why we had these things well separated, says that the number of centers in each cell is a constant. And this is what governs the constant we use in local search analysis. So we have constant size parts. Suppose for a moment we could actually swap these parts. They're not balanced between local and global optimum, but if we could swap them, we can easily see how we can assign points according to the partitioning scheme that we mentioned. So focus on a data point J, and let's say that I and I star are the two centers serving it between local and global optimum. If they're really far apart, so at least di over epsilon, well, in the part where you close I, the reasonable backup plan puts something within O of di around I, and that's good enough already to look like the epsilon that we wanted. Because we said it needed to be epsilon times the total distance between J and its two centers. Otherwise, if they're reasonably close to each other, well, they'll be in the same part with really good probability, at least 1 minus epsilon. So either I star or else its filtering witness will be in the same part as I with probability at least 1 minus epsilon. And that's it for the partitioning scheme, apart from fixing a couple of minor small issues. And these are easy to fix. So the cells might not be balanced between local and global optimum. I did promise a full partitioning of all centers, not just the ones that survive the filtering. And the aspect ratio of these radii might be unbounded. So the first one is easy to fix. First, let's just bring in all of the filtered out centers and consider them as forming their own singleton part of the partition. So we get a full partition of everything. The parts have constant size, and there's the same number in total between local and global optimum. So a simple pigeonhole principle exercise shows that you can cobble together these parts into still constant size parts that are balanced. So balancing the parts is not much of an issue. It's also not too hard to lift the bounded aspect ratio assumption either. And it's just we're going to use a random bucketing scheme. So geometrically partition the centers based on their radius, using a random geometric offset. And the aspect ratio of each part will be some constant, large enough to make sure the bad events happen with probability epsilon. And within each of these parts, we'll consider a random grid instead. The only other thing that bears mentioning is these matched pairs we want together. They could also be separated by this random geometric partitioning. But again, this happens with very low probability because if you look closely at the definition of a matched pair, their radii are within an epsilon factor of each other. And if they are severed, we'll then just move the global op center to the local op center for each matched pair. And that's how you partition things to prove this partitioning theorem. Now, I also want to mention that this allows us to incorporate opening costs as well because we have a perfect partitioning. Every local op center gets closed once. Every global op center gets open once. And if you're in the case of uncapacitated facility location, just don't bother balancing the parts. And in doubling metrics, well, we have nice tools from, I guess, Talwar gave them to us to emulate the essential properties of random grids we need. So you can abstract out what we use for random grids, and we have these tools in doubling metrics. So just want to summarize the two works. We get p-tasses for k-means in doubling metrics and minor closed metrics. So this includes constant dimensional Euclidean metrics, which are of really high practical importance. And some facility location p-tasses that don't fit on this slide, too. So some directions for future work, given the great practical importance of the k-means clustering approach. It would be interesting to get some faster p-tasses for this problem. So in particular, can you offload the dependence on epsilon and the dimension to a constant in front of n, the size of the instance, and just have it be n to some absolute constant? Based on the hardness results we know already, this would have to depend roughly doubly exponentially on d and singly exponentially on 1 over epsilon, unless you could solve sat in sub-exponential time. But nothing rules this out yet, though. I like this particular question about just look at the plane. Is there a near linear time p-test? And then for UFL, I guess Vincent mentioned this earlier, one thing that's kind of slipped through the cracks is getting a p-test for minor closed graphs when you have non-uniform opening costs. Thank you very much. Hey, yes.
Question about the sort of problem statement for how different do the results on, say, k-means and k-median imply anything about like agnostic learning of mixtures of, say, Gaussian or Laplace distributions, or the sort of MLE optimization problem corresponding to what statisticians try to do when they're fitting on mixtures?
So,
I don't know.
Yeah, I think there is no direct connection between those two things, and I think it's a nice direction to actually prove a connection between those things, because that's I think that's the original motivation for k-means, right? So, yeah, one of them, yeah, but we lack this connection actually, and maybe it's possible to prove one.